Hello, fellow students, and welcome to this graphs introduction lecture. So we are going to review some basic concepts about graphs, and then we are going to progress to more advanced topics. Please stick around and enjoy yourselves. We're going to start. Okay, so let's start with the basic concepts. Right, and the first question that I have here is if a symmetric matrix can be the adjacency matrix of a directed graph. A matrix is just a set of numbers arranged in a rectangular shape that usually represent some kind of relation, right? Probably we will want to do some operations with those numbers. Then to answer this question, we need to define first what is the transpose matrix. And the transpose matrix is just a matrix where we exchange rows by columns, right? So it is the matrix where the element, let's call it A sub ij from the original matrix is transformed in the element A sub ji from the transpose, right? So it's we exchange rows by columns, well, rows and columns, right? So for instance, if we have this matrix like something like -8, 2, 3, 7, right, let's call it A. The transpose of this matrix is we just need to exchange, right, rows by columns. The elements in the diagonal stay the same, and here we change the 2 and the 3, right? So this is -8, 3, 2, 7, right? Something like this. And this is the transpose. Right, so what is the element A sub ij that we are talking about here? Right, what is this? Well, if you see the matrix, we can classify the elements by the row and the column where they belong, right? So for instance, here, this is the first column and this is the second column. And this is the first row and this is the second row, right? And the same for the other matrix. First column, second column, first row, second row. So for instance, the element A11 is -8, right? Because it is the element that is in the first row and the first column. Now what the definition says is that for any element for any position belonging to the matrix, the element that we have in the position ij is equals to the element that we have in the position ji in the transpose. Right, so let's check if this is true, right, in the matrices that we have there. So the element 1, 1 in A is -8, right? And this is equals to the element 1, 1 in the transposed, right? As you can see, in the diagonal, the elements don't change, right? They remain the same. If we go to the position 1, 2, the first row and the second column, the element that we have here is 2 in A, and in the transposed, this element is in the position 2, 1, right? So in the transpose is in the position 2, 1. In the second row and in the first column. Now we go to the element 2, 1, which is in the second row and the first column, and it's 3, right, in the first matrix. And this is the element that is in the position 1, 2 in the transpose, right? So it is correct. And finally, the last element, the element that is in the position 2, 2, which is 7, right? And this is the same in the original matrix and in the transpose, because in the diagonal, they don't change. So as you can see, this is the transpose matrix, because for any element, for any yj belonging to A, we can say that A sub ij is equals to A sub ji in the transposed, right? So this is correct. Well, the next step is to define the symmetric matrix. The symmetric matrix, it is the square matrix that is equal to its transpose. Right, so for instance, if we had this matrix, which is -8, 1, 3, 1, 7, 4, 3, 4, 9, right, you can see how the transpose will be the same as this matrix. Okay, let's call it M. Okay, so this is equals to the transpose. Why? Because for every element in M, every element ij in M, this is equals to the element ji in the transpose. right, as you can see, for instance, the element 1, 3, right, which is the number 3. Remember that to count the elements, to identify the elements, we assign a number to each column, and we assign a number to each row, right? So, for instance, this is the element 1, 3, right? The element that is in the first row and in the third column. So we could say that the element that is in the first row and the third column of this matrix is 3, and this is equals to the element that is in the third row and the first column in the matrix, in the transpose matrix, right? So, as you can see, it is the same as this element, right, in the transpose. And as you can see here, right, it is the same. So we have 3 and 3, we have 1 and 1, and we have 4 and 4, right? This is a matrix that is symmetric. It's symmetric with respect to the diagonal. The elements in the diagonal, we don't care about them because they stay in the same position, right? If we take the element 2, 2, for instance, that is 7, we can see how the element that is in the position 2, 2 of the matrix is 7, and it is the same element in the position 2, 2 of the transposed, right? Because when we exchange I and j, they remain the same, right? Because in the diagonal, they have the same value. So this is the transpose matrix, right? And finally, we are going to see what is the adjacency matrix. Right, so it is the matrix where the position IA identifies the number of edges with origin in the node I and destination in the node J. So let's see an example. Let's draw a graph, right, with just 30 nodes. And let's do the adjacency matrix, right? They ask about a directed graph, a digraph. So we need to put arrows, right? The links. Okay, and let's call it D. So if we calculate the adjacency matrix of D, and each node here, we assign a number to each node, right? So for instance, there is no link between B1 and B1, right? There is no loop here. So we put a 0 in the adjacency matrix. We have no link from 1 to 2, right? So we put another 0 here. And we have a link from 3 to 2, right? We have a link from 3 to 2. So in this case, we put a 1 in the adjacency matrix. We go to the second row, right? And this is related to the second node, which is B2. We have a link from B2 to B1. We don't have a loop in B2, and we don't have a link from B2 to B3, right? So it's a 0. We go to the third node, B3, and we have a link from B3 to B1. We have a link from B3 to B2, and we don't have a loop on B3. So this is the adjacency matrix of D. Now, the question is if a symmetric matrix can be the adjacency matrix of a digraph. So first, as you can see, this matrix is not symmetric. Why? Because we have 2 1s here, right, in the position 2 1 and the position 3 2, and we don't have 1s on the symmetric positions, right? So if we write this, right, in the position 2 1, we have a 1, but in the position 1 2, we have a 0. Then in the position 3 2, we have another 1, and in the position 2 3, we have a 0, right? So it means that this matrix is not symmetric, right? Because of these 2 elements and these 2 elements, right? They should have the same value, right, for it to be symmetric. So now the question is it possible that this matrix is symmetric, right? So let's write here. This matrix is not symmetric because the elements in the positions 2 1 and 3 2 are not the same as the ones in the positions 1 2 and 2 3. Right, so for it to be symmetric, we have two options, right? We have two options for it to be symmetric. It could be that we put ones, right, where we have zeros, right? So it could be something like this. Or it could be the opposite. Okay, so we put zeros where we have ones. Okay, so what are the graphs related to these matrices? Right, so this on the left is similar to the one that we already have. But we have two links more, right? We have two links more. One that goes, let's mark them here. One that goes from 1 to 2, right? So something like this. Another one that goes from 2 to 3. So it should be something like this. Right? So this is, let's call this graph B. This is the adjacency matrix of B. And in this case, we have changed these ones, right? So this matrix is also symmetric. And in this case, the graph is something like this, right? We have B1, B2, and B3. And we only have two links, right? We have a link that goes from 1 to 3. And we have a link that goes from 3 to 1. Right? Let's call it C. So this is the adjacency matrix of C. Okay, so as you can see, yeah, a symmetric matrix can be the adjacency matrix of a directed graph, but not always, right? Not always. In this case, what is the difference between these graphs and the one up there, right? This one that is not, where the adjacency matrix is not symmetric. Well, the difference is that each time that we have a link that goes from one node to another, we need to have a link back, right? Because that means that we will have the same number in the symmetric position of the matrix, right? So if I have a link that goes from 3 to 2, I will have a 1 in that position, but I also need a 1 in the position 2, 3, right? In the symmetric position. So let's write it down. just to summarize. Right, these matrices are symmetric. So a symmetric matrix can be the adjacency matrix of a directed graph. The condition is that for any link, right, any link being A and B, two different nodes, because otherwise it would be a loop if they are the same. There is also a link from B to A. Right, so this is the answer. So let's see the second question of this problem. Okay, so the next question is, if an asymmetric matrix can be the adjacency matrix of a no-directed graph. Right, so I mean, we can put a simple example, right? What is a no-directed graph? Right, in a no-directed graph, we don't have arrows. We have these links, which mean that there is a link from B1 to B2, and there is a link from B2 to B1, right? Because the graph is not directed. So how is the, let's call it G. So how is the adjacency matrix of G? Right, in this case, we only have two nodes, so we only have two rows and two columns. And there is no loop in B1, so there is no link from B1 to B1. There is a link from B1 to B2. There is a link from B2 to B1, and there is no loop in B2, right? So this is the adjacency matrix. So it's very obvious that this matrix will always be symmetric, right? Because if we have this directed graph, it means that we have a relation in both ways, right? From B1 to B2 and from B2 to B1, right? So this matrix will always be symmetric. So let's write the answer. Symmetric matrix cannot be a no-symmetric matrix, cannot be the adjacency matrix of a no-directed graph. Because any link from A to B, being A and B to different edges, right? Because if it was two different nodes, right? Because if they were the same node, we could be talking about something in the diagonal that we don't care about because it's always symmetric. Increases in one unit the position AB, the value, right? Value position AB, and BA, value in the positions AB and BA, being MA, the adjacency matrix of the graph. Right. In the case of having a link in the node B, for instance, right, like a loop, it would increase one unit value in the position BB of the adjacency matrix. So it's on the diagonal, right? So consequence, the adjacency matrix must be symmetric for a non-directed graph. Okay, so this is the answer, and let's see the next question. Right, so the next question says, C, describe an example of a graph where the directed version of this graph has an odd number of edges. Okay, so if we have, let's imagine that we have this graph, right, Y. If we make the directed version, it will have two edges, right? Two links. It would be something like this, right? So for the directed version, right, we must put one link from B1 to B2 and one link from B2 to B1. Right, so it's an even number of edges. So to have an odd number of edges, we need to have a loop, right? Because otherwise it's impossible with a non-directed graph, right? If I have this, for instance, right, in the directed version, we will have 4 edges. So the only possible option is to have a loop, right? So let's put a loop here in 3, and let's call it G, and let's do the directed version. So to do the directed version, we put the same nodes, and we transform these bidirectional links to one directional links, right? So we have a link from 1 to 2 and one link from 2 to 1, right? And here it is the same. We have a link from 3 to 2 and we have a link from 2 to 3, right? Now the difference is that in the loop, we only have one link, right? Because this link establishes a relation between 3 and 3, right? And so it's the same thing that we are doing here, right? So this is the example of a graph with the directed version having an odd number of edges, right? So here we have 3 edges, and here we have 5 edges, right? So the first exercise is finished. Okay, so that's all for today. Thank you for listening to the video. If you have any question, don't hesitate to ask in the comment section. Also, if you notice any mistake or any bug, anything wrong that I said in the video, please let me know in the comments. That's all for today. I will see you in the next video. Bye-bye.